So whether you are using a nonlinear commercial nonlinear finite element code or writing your own code, I think it is necessary to understand the essential structure of a nonlinear code, which is, by the way, very similar to um, linear code with a few but important modifications. Now, before we go into forming tangent stiffness matrices and internal force vectors for um, specific constitutive models, which we will do in the coming weeks, let me describe in this lecture the essential structure and the essential steps involved, essential calculations involved in a nonlinear FEM code. Now, this is kind of the algorithm, which is very similar, as I said, to a linear finite element code. But here you start by initializing time, and then you have a time step. You increment the time. You have a loop over time, which is a big loop, and then you increment the time and form the external force vector based on the body forces and surface tractions and forces that you have applied at time t. Form the external force vector, set delta u equal to 0. Delta u is the quantity that we are going to solve in this time loop. So delta u is the increment in displacement between time t and t plus delta t. Now, to calculate delta u, you start this Newton-Raphson iteration loop, which is special to non-linear code. In linear code, you don't need to do the Newton-Raphson. You do a one-step inversion to get the u. So you start the Newton-Raphson iteration, and then within the Newton-Raphson iteration, you loop over all the elements. You localize the variables. That means from the global array of displacements, stresses, and so on, you collect those variables which pertain to the element that you are looking at. And then for that element, form the tangent stiffness Ke, local tangent stiffness, element tangent stiffness, and the element internal force vector Fe. So you assemble them into the global, and this goes on for each and every element in the system. Now, after assembling it, and this is similar to any other finite element program, you modify the global stiffness in RHS for boundary conditions. We have learned how to do this in our basic finite element courses, and the process is no different here. After doing that, we solve for u, not for the total displacement u, but for the incremental displacement delta u. Then we update the internal force. So this delta u, we add it to the u of the previous time step and update fint, and then check if fint and fxt are close to each other by some norm that we have fixed. If they are not closed, then this delta u is not the correct delta u for this time step. We go back and we do more iterations. We restart, go back to this point, we do more iterations, and we keep doing these iterations till f internal and f external become sufficiently close. Now, once they become sufficiently close, then we have got the delta u that takes me from time t to time t plus delta t. I've got the correct delta u that takes me from time t to time t plus delta t, and I update the u. Just add this delta u, which is the correct converged delta u, then loop over all elements and update the stresses and other Gauss point variables based on this new displacement, new set of displacements that I have found, output variables if necessary, and then the time loop ends. I go back to the beginning of the time loop, increment time again, and then continue the process. So this is the essential structure of a nonlinear FEM code, and as you will see, the main differences are the following. We are solving for delta u rather than the total u. We have a Newton-Raphson iteration process in place within which we form not the total stiffness matrix, but the tangent stiffness matrix and the force vector, internal force vector. And the rest of the procedure is more or less the same. One more change is that you have to check for convergence by checking if internal and external forces are close enough to each other. So this is the basic structure of a finite element code, and let us now try to see it from somewhat a few different angles. It's basically the same thing that I'm going to discuss, but from a few different angles. Let us try to understand the process a little bit more. So suppose we are doing the updated Lagrangian technique. This is our initial configuration omega 0, and this at this point time is equal to 0, and this is our last converged configuration, uh, omega tk, which is at time t equal to tk. Last converge means that for every point in this configuration, we know the u's, which we call uk, and these are the displacements, and xk gives the position vectors of each and every point. So this uk is known for this configuration correctly, such that if I plug uk into the virtual work equation, then I will get del w equal to 0 for an arbitrary delta v. So this means this is the last converged configuration. Now, given this last converged configuration, I want to find the configuration at time t equal to tk plus 1, which we don't know. And to find this, we need to find uk plus 1, which is the displacement of this same point from the reference configuration. And to find uk plus 1, I need to find this delta u, which is the increment in displacement, which will take me from the configuration omega at tk to the configuration at omega tk plus 1. And I have to, how do I know that this, I have found the correct delta u? I will know that when uk plus 1, which is uk plus delta u, for an arbitrary delta v, will give the virtual work, total virtual work, to be equal to 0. So if I satisfy this equation, I'm trying to solve for uk plus 1. Actually, I'm solving for delta u, because if I solve for delta u, I can add it to uk and get uk plus 1. I'm trying to set that delta w of uk plus 1 for an arbitrary delta v has to be equal to 0. When that happens, I would have found the correct delta u, and if I add the correct delta u to the previous uk, I get uk plus 1. And if I know uk plus 1 at all points on this configuration, I will be able to reconstruct the configuration at omega tk plus 1. So let us try and understand the process in a little more detail. So here the last converge step was this, which means that I have an uk, a global uk, that satisfies this equation. Now I want to solve this equation by finding a uk plus 1 that sets del w equal to 0 for an arbitrary delta v in both cases. Now, so this equal to 0 is something that I have already achieved. So this internal virtual work is equal to this external virtual work. uk is known. Now I want to achieve this del w equal to 0. So I want this internal virtual work with uk plus 1 to be equal to this external virtual work. Now this is how the procedure goes. In this, the shaded thing is elemental step. I'll explain what that means. So this is only for the Newton-Raphson iteration. So for the 0th iteration, I equal to 0, and most often we set the first guess or the 0th guess for uk plus 1 to be the already converged value of displacement, that is uk. So that is what we set. Now while del W for UK plus 1 is greater than a small tolerance, we do this step for each and every element. Then we assemble the results of this step. That means assemble the left hand side and the right hand side. After doing that, we update. So at the end of that process, we get uh, a new vector, new velocity displacement increment delta ui. We add that to the ith iteration to get the value for the I plus 1th iteration. We update the iteration counter, carry on this process, and finally when the process is over, we have a correct value of uk plus 1 at our disposal because of successful completion of this loop, and we set that to be equal to uk plus 1, and then if required delta u, triangle u can be also stored as uk plus 1 minus uk. These are at the end. This is the end of the time step. Now this is the Newton-Raphson step, where I am trying to set del w of uk plus 1 for an arbitrary dv to be equal to 0. To do that, I have to, the Newton-Raphson step is the the directional derivative of delta w in the direction of delta u has to be equal to minus del w, and this del w has to be calculated at the ith interval, ith iteration of uk plus 1, and so does this. So this calculation will yield this iteration or the ith iteration to triangle u, and that will again be assembled and go into this step. So this step is the crucial step where this quantity, which is the tangent stiffness, is solved, is inverted for solving this quantity, and that quantity then is assembled and added to the global displacement vector, and this carries on. During a Newton-Raphson process, del V does not change, and so what we have is the configuration at time tk, which is the last converged configuration, and this is an element in that configuration, and at each node we have some value of delta v applied. So for all nodes we have, for the ith node I have shown this, and now the goal is to get to this configuration, which is the k plus 1th configuration. Now to do this, what Newton-Raphson does is it does several iterations. So in the first iteration, where the delta u comes out to be delta ui1, that means delta u at node I at the first iteration brings it here, the second iteration brings it here, and the third iteration brings it here, but all the while this virtual velocity is not affected by this quantity and remains the same, and this is an arbitrary virtual velocity, which, as we will see, will fall out of the calculations, and setting del w internal equal to del w external is equivalent to setting f external global is equal to f internal, because this is an arbitrary quantity. That's why this leads to this. We have already shown this, and this is what will be used to calculate the tangent stiffness. Again, further detail. Again, the shaded box is the elemental step. That means whatever comes out of this has to be assembled in order to go to the next step. I'm not talking about the assembly process. I'm assuming you know that already. Again, this is the Newton-Raphson loop. First iteration is 0. Take the last converge step and put it into the first guess for the k plus 1th step. I am now using this for u because this is a vector containing the components of u. That's how we store it in finite element. So we have converted this u to Voigt notation, and I'm storing it. That's why I'm using this curly brackets to denote it. So dump all that as the 0th iteration. Then while internal force and external force are greater than some small tolerance value, do this elemental step. And in this elemental step, we we take this equation F internal u minus F external u equal to 0, and calculate the calculate the Newton-Raphson linearized form for this. So d of f int minus fx in the direction of delta u is equal to minus f int So this is what Newton-Raphson, this is what you will need to do in Newton-Raphson to find this triangle u. So we'll find triangle u for the ith iteration. So that's here. We'll have to take the directional derivative at the ith iteration of uk plus 1, directional derivative of external at the ith iteration of k plus 1, and on the right hand side we have f int minus fx also calculated at the ith interval of uk plus 1. Now again, this is your tangent stiffness. This will have to be assembled. This is your right hand side. This will have to be assembled as well, solved, and then you can do this step and carry out the remaining steps. One more thing that I want to mention here is most of the time we will assume that our F external is independent of U. That means we will deal with configuration independent forces for most part of this course. There are important situations where the external forces can be configuration dependent, but we will not consider those for the time being. So this will identically be always equal to 0. To get the tangent stiffness, we will only have to linearize, we only have to find the directional derivatives of the internal force at u k plus 1 in the direction of delta ui. That's the only thing that we'll have to do, because we will take configuration independent external forces.